Hello everyone, this is Poornima Deepthi working as an assistant professor in the Department of Electronics and Communication Engineering in MLR IT. So, today's topic is signal description of 8086 or pin configuration of 8086. This video is the part of the subject microprocessors and microcontrollers. So, coming to the overview of today's topic, signal description of 8086 and pin configuration of 8086, and what are the pins present in the minimum mode of 8086 and what are the pins present in the maximum mode of 8086. So here we already know that the 8086 microprocessor is having the 3 clock rates for 5 MHz, 8 MHz and 10 MHz for 8086, 8086-1 and 8086-2. Different processors are having different clock rates, and it is a 40-pin dual inline package. So it can operate in multi-purpose configurations, like it can operate in minimum mode as well as it can operate in maximum mode. So if the application is having more than one processor, then it can consider as a maximum mode. And if only one processor is present in that particular configuration, then it is considered as a minimum mode. So this is the pin diagram of 8086. Here we are having two VSS pins, ground, and one power supply pins plus 5 volts power supply is needed to operate 8086 microprocessor. And to give clock pulses, we are having one pin, clock pin, and the remaining pins is having its own unique features. And these pins are having dual features when these are considered in the minimum mode and these particular pins are in the maximum mode. So now coming to the pins present in the 8086, as we all know that the 8086 microprocessor is having 20 bits address lines which starts from A0 to A19. And data lines are of 16-bit which starts from D0 to D5. Out of these A0 to A19, the pins which is present in A15 to A0, A0 to A15 and D0 to D15, these are time multiplexed. So whenever we need address, we can get the address from these pins, and whenever we need data, we will get data from this address and data enabled pins. So how to enable address and data, and what are the pins used to time multiplexed address and data lines? These are the pins from AD0 to AD14 out of here, and here AD15. These 16 pins are time multiplexed address and data pins which can be used for the address as well as data. So when we will get address and when we will get data, and which pin enables address and which pin enables data. Here, to get address, actually to execute an instruction in 8086, we are having 4 clock cycles. We need 4 clock cycles. T1 is the first clock cycle, T2 followed by 3, and there is a wait cycle and then T4. The first clock cycle, T1, in every instruction, T1 is only used to check the address of that particular one. So here from pin number 16, 1 to 2 to pin number 16 and this 39th pin. These pins, out of these address and data enabled pins, here the address is only present in the T1 clock cycle, whereas the remaining will have the data over it. So only address is present at T1 state of the clock cycles, and the remaining will followed by the data. So which pin is used to enable this this address and data lines? Here we are having ALE pin which is used to enable address. If ALE equals to 1, then address will be available in these AD0 to AD15 address lines. Address and data lines. The remaining time, if AL equals to 0, then we can say that data is present over these pins. So this is all about address and data lines. These are address and data lines are time multiplexed lower order address bytes, and here we are having D0 to D7 and DA to D15 or D0 to D15. These are the data lines presented. And coming to the remaining, out of address lines 20, we have been know that A0 to A50. The remaining A16 to A19 are available here. A16 to 38 pin to 35 pin. Along with the address pin, there are status lines which specify some specifications. So here A16 pin is with S3, and out of this, when in the first T1 clock cycle, A16 and A17 pin will provide the address for that particular pins, out of that particular pins, and S3 and S4 provides the status of which segment has been accessed. Here, this is the table which provides the data when we are getting the extra segments have been selected. When S3 and S4 pins, here if the pin is 0 and S4 pin is 0, then you can say that extra segment is accessing. So when S3 is equals to 0 and S4 is 1, you can say that code segment is accessing. If we are having 1 and 0, then stack segment has been accessed. So if we are having 1 over S3 and S4, then you can say that data segment has been accessed. So this is the status line. So out of first clock cycle, address will be provided here, and the remaining T2 to T4 clock cycles, here the status will be provided through the pins. So coming to the next pin, it is BHE bar or S7 pin. Here BHE bar is bus high enable pin, where higher order D8 to D15 bus will be provided. Higher order data can be accessed if we are having bus high enable. As you all know that here it is BHE bar. Bar indicates it is a negative logic pin. So if BHE bar equals to 0, then only higher order bus can be accessed. Apart from that, if we are having accessing S7, so S7 signal is present in T2 to T4 states. Next, coming to the MN and MX bar pins. This is the pins used to fetch the microprocessor for the minimum mode or maximum mode. If this pins MN equals to 0, you can say that MN bar or MX bar equals to 0, then we can say that microprocessor is accessing the maximum mode. If this pin equals to 1, then it will be in the minimum mode. So if MN or MX bar is equals to 0, then you can say that it is accessing as the maximum mode, and if it is equals to 1, then it will be in the minimum mode. Next, RD bar. RD bar, it is also a negative logic pin, and it indicates that read operation is performing. So you can say that what is the read operation means? You are getting the input from the memory or input output devices. So where you are getting the data from the memory or input output devices will be followed. We can know by using that memory or input output pin. So here RD bar is a read pin which is used to take the input from the other peripheral devices like input or output devices or memory devices. Next, test bar and ready. So here test bar. As you all know that microprocessor is a fast processor. So the other peripheral devices which we are connecting to the microprocessor will we need to match the speed with the microprocessor. As we all know that the other peripheral devices which is we are interfacing to the microprocessor can be called as slow devices. Like if we take one example of a printer, a microprocessor can give the instruction like print 100 papers to the printer. Printer will will not print as the microprocessor speed will not match the printer. So a printer need to take some time to print 100 papers. So until then this microprocessor need to be in the wait instruction until the other peripheral devices has completed its operation. To match the companion, to match the speed with the other peripheral devices, until then the processor need to be in the wait state. To test bar is to examine by the wait instruction. So here ready is nothing but it is getting the acknowledgement from the slow devices or the other peripheral devices which is attached to the interface to the microprocessors, that they have completed the data transfers or they have completed its job and they are ready to transfer the data. Next, coming to the reset operation. So here reset is a pin which is used to terminate the processor's current execution, and after reset instruction the other registers will get into the 000 location, whereas IP and CS will get into FF location and 0000 location. So to calculate the physical address, that we need to take the 4F's condition here. And then coming to the INTR is a interrupt request pin. So interrupt request pin. So if any interrupts are occurring while executing a program, then this INTR pin will get those interrupts. So if any other peripheral devices are causing the disturbance to the microprocessor, then microprocessor getting the interrupt request. So whether to accept the request or to deny the request will depends upon the microprocessor, and this acknowledgement, whether it has been accepted the request or it has denied the request, will be given out as a INTA, interrupt acknowledgement pin. Another interrupt acknowledgement pin is there. So in that interrupt acknowledgement pin, this processor gives the acknowledgement back whether it has accepted the request of interrupt or denied the request. If IF, interrupt flag, is equals to 0 and INTR, if we are getting INTR as 1, then INTR will access the interrupt. If IF, interrupt flag, is 0 and INTR equals to 1, then it will be disabled. INTR won't allow the interrupt. And then coming to the NMI, non-maskable interrupt. Here comes the most prioritized interrupt in the 8086. Non-maskable interrupt. We can't hide this interrupt or we can't deny this interrupt. If this interrupt occurred, the processor need to execute the current running instruction and it need to jump to that particular interrupt service routine, and it need to access the interrupt specified as a NMI interrupt, non-maskable interrupt. This is the most highest prioritized interrupt in the 8086 processor. Next, coming to the pins specified in the minimum mode pins. Minimum mode. What are the pins are? Hold and hold acknowledgement. Here, hold acknowledgement is the other processors, if they want the system bus, then the other peripheral devices or other processor need to ask the microprocessor to free the system bus. So that is this pin will get that request. And if the pin is, if the processor is accepting the request and it is sending the bus, system bus is available for the other processors or other peripheral devices, will depends upon the acknowledgement given from the microprocessor. If it leaves the system bus, then it will give hold acknowledgement that yes, system buses are ready, you can access that. If it doesn't allow the system buses, it will also acknowledge through this acknowledge pin. If the other peripheral devices want the system buses, it approaches through the hold pin and processor gives the acknowledgement through hold A pin, HLDA pin. Next, coming to WR bar. This is the write operation. It is also an active low pin. So here if we are having 0 over here, it is saying that it is sending the output to the other peripheral devices. Either it is sending output to the memory device or output devices. So here M or IO bar. So here this is memory or input output bar. If this pin equals to 1, then you can say that memory, we are either getting the input or we are sending the output to the memory. If M or I naught bar is equals to 0, so the operations are performing through input output devices. Whether we are getting the input or whether we are sending the output, that will be into the input output devices. And here DT or R. Here we can say that DT is the data transmit. So here if it equals to 1, you can say that data has been transmitted, or equals to 0, you can say that data has been received from the other peripheral devices. Then DEN, data enable pin. This pin is an output enable. If we are connecting 8286 or 8287 minimum system to which is used for the transceivers. So DEN is active low during each memory and input output access, and for INTA, interrupt acknowledgement cycles also. So coming to the ALE, address latch enable. As I already told you that to get the address over AD0 to AD15, so here if we are having ALE equals to 1, you can say that it is having the address over these pins. If it equals to 0, you can say that data has been accessed through these pins. Then coming to the INTA, this is the acknowledgement given by the microprocessor whether it is accepting the interrupt request or whether it is denying the interrupt request. So these are the pins which is used for the maximum mode microprocessors. So the hold and hold acknowledgement will be related to this. So if the other peripheral devices are accessing wants the system bus, then it will ask the processor, it will send the request through RQ bar. And the processor need to grant the request or it needs to send the acknowledgement, it will acknowledge through using grant GT1 and GT0. Here lock bar. So it is an active low pin. What is lock bar means? If the processor, if this equals to 0 means it is it is a negative logic pin. So if it is equals to 0, it enables. So when it is in the enable position, the other peripheral devices cannot ask the microprocessor, cannot get the system buses from the microprocessor. Microprocessor will lock the system buses and it will not share the system buses with the other peripheral devices. Next, coming to the pins S0, S1 and S2. These are the status lines, status pins which provides which is used by the 8288 bus controller for generating all the memory and input output operations. Whether memory is reading or data or memory is writing the data or input output devices, which device is giving input or when the output is getting to the input output operations. This status will be present in this S2, S1, S0. This is the table which represents the operations of S2, S1, S0. This is the status lines. If these three are equals to 0, then you can set interrupt acknowledgement, INTA pin will be accessed. If 0, 0, 1 is over these pins, then you can set it here. It is reading, like it is getting the input from the input output ports. If it equals is 0, 1, 0, then you can say that it is giving the output to the input output port or writing the output into the input output port. If it is 0, 1, 1, halt will be there, like no operation will be, processor stops the operation. Here 100 means it is accessing the code. If it is 101, then read, memory read operation will be performed. If 110 is there, then you can say that write, output is writing into the memory. If all triple ones is there, then that is passive state. Passive state. So this is the status lines which present whether the memory read operations or write operations are performing or the input output read operations or write operations are performing. So next, coming to the next pins QS1 and QS0. This is the status pins which shows the operations performed in the queue. Queue which is already present in the architecture of 8086, which prefetches the instruction and stores the instruction for the further execution of the program. So coming to the status, if QS1 and QS0 are having zeros, then no operation will be performed. If it is having 0 and 1, then first byte of opcode has been stored into the queue. So first byte is in the queue. Next 1, 0, so queue is empty. Like all operations are completed and queue is not having any opcode in that. And 1, 1, already first byte has been from the queue, opcode from queue. So the subsequent byte will be moved from the queue. This is the status which shows the operation performed in the queue. So out of all, these A02, AD02, AD15 pins are used to provide the address and data over the processor. If ALE is equals to 1, then address will be provided in it. And if it is ALE equals to 0, address latch enable equals to 0, then you can say that data will be present in these lines or pins. So here NMI and INTR, non-maskable interrupt, highest prioritized interrupt in the 8086. INTR is the interrupt request and it will give acknowledgement through INTA. Here S3, S4 will specify the status of which segment has been accessed. BHE bar bus high enable, it will have the highest order of the data, minimum maximum pins, read operation, request GANs similar to the hold and HLDA, and lock bus to lock the bus, and this is used to which memory operations or input output operations are specified, and these two pins has been used to showcase the status of the queue. Test bar and ready are for the external devices or slow peripheral devices which has been interfaced with the 8086, and reset all the program, and all the registers has been cleared. And coming to the write operation, here memory and input output, data transmit or receiver, data enable. 8086 will give the acknowledgement to the interrupt request. Until now, we have discussed about the pins present in 8086 and what are the pins we are having in the minimum mode of 8086 and the pins present in the maximum mode of 8086. Thank you.